So I'll be talking about something that I've been working on and off for like 5 years. So it started before I joined Sparsity to work on this. And then last year I was able to actually really put some code down to solve this issue. And I'll be talking about how we now much more fully support sparse data in the tidymodels ecosystem. So as a motivated example, what we have here is we're loading the flights data set. So this is all the flights coming out of New York in the year 2013. So it's around 300,000 flights, a little bit more than that. And we're building, it's not a great model. What we're trying to do is predict whether how much the delay will be, and then putting it into an XGBoost model and seeing what happens. And we're also doing some pre-processing, and most of it is just to handle some missing data and handling variables, labels that haven't seen before. But the important part here really is the step dummy. So we're creating dummy variables of all the theoretical predictors. And right before anything happens, there's 18 predictors. Once we add the dummies, there's a little over 4,000. Because some of these, couple of the theoretical variables is like the tail number. So we'll have a dummy variable for each plane that ever flew out of New York City in the year 2013. So this means that this data set is quite sparse, meaning there's a lot of zeros. It has over 99% zeros, which are mainly concentrated in these dummy variables. So if you ran this, if you try to fit this model a year ago, it would take around 8 minutes to run. And this is nothing to do with XGBoost. This is only something that happened because of what we're doing in tidymodels. And now we're actually seeing some improvement in the time it takes to fit. And you might think that if we got it down to 100 seconds, that would be really, really nice. But that's simply not true, because now it runs in 4 seconds. And this is nothing to do with XGBoost being slow before and fast now. This is simply us being able to fully leverage the sparse data that XGBoost really supports. And to tease a little bit why this has happened, because we're now allocating a lot less memory. And the rest of the talk will showcase how we made this happen. Right. So first we'll talk about alt-rep, a little side thing, something that happens in base R. So alt-rep is short for alternative representation, and it's something that happens in R at the C level that you shouldn't know happens. It always happens under the hood. If anything, it's really hard to actually see if something is alt-rep or not. And it has a lot of different use cases I sadly don't have time to talk about, but I'll talk about the first one that really links to it, which is the idea of an integer sequence. So we've all been making them. If you have a for loop, anything else, it's a sequence from one integer value to another integer value. And this uses alt-rep under the hood. So if we try to look at how much memory a vector takes up in R, I'm using the lobster package because it's easy. The numeric function just produces a bunch of zeros. And we can see that as we are making the vector 10 times longer, it also takes up 10 times more memory in. But if we're now making a sequence of the same lengths, but then as before, but we're increasing them, they always take up the same amount of memory in space, regardless of how long you're making it. So you could make one sequence that's so large that it actually wouldn't fit in memory on your computer, and it would still only take 680 bytes. So what's happening is here we're just imagining it's a small sequence, but it shows everything. So how would we describe everything about this vector in as few values as possible? And to be able to do that, we need to know how long is it, how many values does it have, what's the first value. So here it starts at 1, and then we have this step. So here it increments by 1. but you should imagine it increments by 2, 4, minus 1. So we can describe any length integer sequence using 3 integer values. And this is what happens in AltRep for us. And with that, whenever some operations happen, and so if you want to say, what's the length of an AltRep vector? Instead of pulling it up and looking at how many values it has, intercepts that saying, hey, you're trying to call length on this AltRep integer sequence, just pull out the first value and return that. So it's constant in time, and likewise with, if you wanted the sum, there's a little bit of arithmetic to do it, and you can now calculate the sum of any integer sequence at the same time regardless of its length. So there's a bunch of different methods we need to implement to be able to have AltRep working. So here we saw there's the sum, and we can also say is something sorted. It's really easy to know if integer sequence is sorted, because if the increment is positive, it's sorted. There's nothing else we need. The last one I want to talk about is the serialized state. So the main thing to know about AltRep is it's very, very fragile. If you're trying to do anything to an AltRep vector that it doesn't support, it will make the normal vector and then use that. So if you try to add 1 to integer sequence, it's no longer an AltRep vector. It's just a normal vector now, and it will do that. All right. Now we can get back to actually talking about what I did. So there's this idea of sparsity. So here we have a sparse vector that has 14 values or something, and 2 of them are non-zero. But the principle is the same if it had 1,000,000 values. So then what's the minimal sufficient amount of information to be able to recreate this vector? And then we need the length. And what we have instead is we want the positions, so the integer position of where the non-zero values are and what the values are. So this vector can now be represented as 5 integer values, and it technically doesn't have to be integer values. You can have a sparse double vector. So then you have 3 integers and 2 doubles. So there's a little bit of trade-off from what we had before, where now how much memory a sparse vector takes up is fully dependent on the number of non-zero values. So if half of them was non-zero, it wouldn't be worth it anymore, because we're actually spending more time, and some of these operations we'll be doing later. It isn't always worth it. So there's a threshold, but it's not a set threshold. It's very fluid. But this is the main idea behind what we're doing. And likewise, we can also do these pseudo calculations that are faster than doing it before. So if we want to get the sum of a sparse vector, we just sum up all the non-zero values, which when we're using it should be a lot shorter than the real thing. And if we want to find the ith element, we just see, is the I in the positions? If it is, we just find the matching value. Of course, this all has to happen in C. So this is the C implementation of the same function from before. And because there's a lot of edge cases needs to happen, and we need a separate one for the integer version and the double version and the character version and everything else. So in this process, I created the sparse vectors package. So as I said before, everything happens in C. So all the AltRep plots into the C interface that R has. It needs to match. Everything has to match. So it's handlings for infinite, not a number, NA values. Everything has to match up completely with what happens before. That's the promise you're given when you are using AltRep. And then they're very fragile. If anything happens, it materializes a normal thing, and it becomes non-sparse then. So we also want to avoid ever doing something to these sparse vectors that isn't supported, because then we're losing the benefit. Additionally, because we need it, It has converters, so if you have a sparse matrix, we can turn it into a data frame with sparse columns in it, so a bunch of sparse vectors as columns, and back and forth. And this is something you don't need to worry about. So this is mainly for us because we're using it across all the packages, but hopefully you shouldn't really know that this happens, but this is where like, all the work really is. So why are we doing this? I spent a lot of time talking about different things, but the reason why we're doing this is sparse matrices and data frames or tibbles don't commingle at all. Additionally, a sparse matrix, by being a matrix, is forced to all the values have to be the same type. So you can't mix factors and integers and dates. It all have to be the same thing. So in theory, you can't do classification with a sparse matrix because you can't have the outcome in it. So you need to have it separate. And secondly, tidymodels is built on tibbles. So if we wanted to do sparse data support with sparse matrices, we would have to duplicate all the code and have two paths, which is not worth it. So to make it all happen in tidymodels, we have to do three different things. One of them was making sure that our sparse data could pass through all the internal functions from end to end. So if you pass it into fit, it can go all the way across without accidentally materializing in a way. We have, as we saw in the beginning, we had this step dummy. It's one of the steps that can produce really sparse data. So we needed to upgrade all the steps that have produced sparse data to actually produce it. And lastly, we have this idea of automatic total, which I will get in details in like 4 or 5 slides. So having things go through is the least interesting part of this. It's just writing hundreds of tests where we try to put in sparse data and then seeing if it stops being sparse at one point, and then figuring out this function did it, right around it, and continue until everything was able to flow back and forth. Secondly, we have a couple dozen steps that are able to work with sparse data. You can also imagine that you can take a sparse vector and multiply it by 2, and it stays sparse because it doesn't remove the zeros. So there's a couple of steps that can modify sparse data or use sparse data or produce sparse data. So all of that happens. And the ones that generate now have received a new argument called sparse that can take 3 values, yes, no, or auto. And auto is the default. And the automatic total is, so we wanted this experience to be as seamless as possible for the users. So you only want to use sparse data when it's beneficial for you. And when we say beneficial, it's mainly computational speed, because it more or less goes hand in hand with the memory allocations that happen. So something can benefit from using sparse data if the model supports it, so not all the engines support it. So like XGBoost, GLM, like LemNet, LibLinear, like GPM will get full support by the end of the month. So some of them support it, but you also need enough sparsity in the data that it's worth it. So we don't want to encode everything as sparse vectors if there's no zeros, because then we're doubling the data and everything becomes really slow. So there is some threshold, and it's a little bit hard to do. But if these 2 questions are right, then we automatically turn on the sparse creation for you, and it should just happen. The way we do the sparsity estimation is we need to know how much sparsity there is before the data goes into the model, but we need to know it before we fit the recipe. So it matters for the model, but for the recipe. And if we have to if we need to do the recipe and try both ways, we lost all the time anyways. So what we are doing, we have a very rough estimate of what the sparsity will be. And for some of them, they're fairly easy. So if you have a dummy variable coming in, we know precisely how much sparsity that will add to the data. So we have a certain number of columns, and a sparsity beforehand, we know it has 10 labels, or 10 levels, so it produces 10 variables that has like 90% sparsity in it. So we'd have a rough estimate of what happens, and then we just do that math, and then we have an estimate of how much sparsity is in the data. I then set up a simulation study that takes around a couple of 100 hours to run, and it is fitting models that explicitly state that they're supporting sparsity, and we're doing different number of rows, number of columns, amount of sparsity, and with that we're fitting a model that says which one is faster. We're then encoding that as a simple model that's then embedded into workflows. So when you're fitting a model, it will estimate, is this model going to benefit from being sparse or not? And if it is, it will turn all the autos into yes, and if it doesn't, it will turn everything into no. It also means that if your model doesn't support it, it doesn't even do this, because it just says, oh, you don't support it, no, right away. So what it means for you, the user, is that we technically also have sparse data support as input. So if you have a sparse matrix, you can fit and predict on it without going through something else. It just natively supports it by turning it into a sparse matrix right as it comes, sparse tibble right as it comes in. And because we're not perfect, the automatic toggle can be turned off or on manually by setting the sparse argument in different steps to yes or no. So yeah, so it basically means when we have this before, the only thing we need to change is setting this to yes. So our little prediction might not have affected it at all. But as far as we know, no one is seeing extreme slowdowns from this, but the potential in speed improvements is really high. And then that's what I have. This is the tutorial to the slides. There's some number of articles on the tidymodels.org website that show how we're doing. There's this blog post, and we have a link to all the currently supported model engines and recipe steps. Thank you.